Hello there, I Dr. Anuj, and today we are going to discuss acidity and basicity of metal carbonylates complexes. Okay, as you know, in last lecture we have already discussed a lot about metal carbonylates, their synthesis and chemical properties. Okay, today we are going to discuss some points related to acidity and basicity. So let's start. Metal carbonates. First of all, metal carbonylates. You know very well that metal carbonyl complexes are those complexes which contain metal direct connect with carbonyl. Maybe number of carbonyl ligand, maybe 2, 3, 4, etc. Okay, so this is metal carbonyl complexes, the complex which contain the direct connectivity between metal and carbonyl ligand, known as metal carbonyl complexes. But when this complex found with negative charge, that means 8, so that's why metal carbonylates. Okay, metal carbonylates 8 due to negative charge. So this is the metal carbonylates. Metal may be transition elements, first transition series, second transition series, third transition, any element may be here, and CO is the carbonyl ligand, and is the number of ligands, CO, number of CO ligands. Okay, or negative charge, this is negative charge which occupy on all complex. Okay, but one thing is here, because COO is neutral ligand, this is neutral ligand, okay, so overall negative charge will occupy by negative charge, so that means this negative charge will be on metal. So in this complexes, that means metal carbonylates, metal will be negative oxidation state. Okay, negative charge species. Okay, so that's why this metal will be negative charged species, negative charged. Okay, so this metal will have negative oxidation state because this ligand is a neutral ligand, so that's why this charge will be located on metal center. Okay, now we are going to discuss acidity and basicity. As you know, the basicity, one thing is also here, you have already stated that metal is negative oxidation state species here, so that's why this metal may be act as base, for a reaction, and maybe it act as a nucleophile, right, for a chemical reaction. We have already talked about this action in last lecture, and the video you can find by description box. I have given link of that video. So today we are going to discuss the role of metal carbonylates as a base. So first of all, we should know about the basicity, which metal carbonylates will act as a strong base and which one will act as a weak base. So that's why today our focus is this. So if metal carbonylates will act as a base, so there is 2 points related to the basicity. Okay, first of all, you need to find the active hydrogen in the reactant. It also known as acidic hydrogen. So first of all, if you are going to make a chemical reaction of metal carbonylates with any species which have acidic proton or active hydrogen, so then this metal carbonate will extract the acidic hydrogen or active hydrogen from the reactant and will form a product. So the tendency to attract the proton from a species of solvent or solution of metal carbonates depend on its basicity. So basicity of metal carbonates will be depend on electron density on negative charge on electron density on metal atom. So central atom the density of electron density on central atom will decide its basicity. Okay, so first point is that basicity directly proportional to the electron density negative charge, because this is negative charge located on metal, so that's why electron density, the amount of electron density will directly proportional to the basicity. High electron density, that means high basicity, that means it has high tendency to abstract the proton from the solution or reactant species. Another point is that basicity will also depend on the easy availability of the electron density, that means easy electron donation power. So electron donation power of metal carbonylates, metal carbonylates. So there are two factors which can define the basicity or the tendency to attract the proton from the reactant species. So these two factors will decide the capacity or tendency of metal carbonylates to abstract the proton from the reactant species. So let's discuss some examples. If you have some example like this, suppose you have chromium and this is cyclopentadienyl ligand, and this is CO, CO, and this is one negative charge. So this that means it is a metal carbonylates, okay, because of negative charge. Otherwise it will be metal carbonyl complexes. And here you have another system similar like this, but a little bit different due to different ligands. So this is CO, but another ligand is PR3 type ligand. Okay. Another example you have this is cyclopentadienyl ring attached with chromium, and this is CO, this is PR3, and this is PR3. Now you need to define which is strong base or the basicity order. What will okay, so what will be the basicity order of three metal carbonylates? You need to design the correct basicity order for these complexes. So suppose this is first complex and this is second complex and this is third complex. Okay, so as you know, the basicity directly proportional to the electron density on the metal. So you need to define in which case chromium have much electron density as compared to others. So which have much electron density, that means basicity of that complex will be high. Okay, so in this case you can see here this is carbonyl ligand, this is also a carbonyl ligand, this is also a carbonyl. So this is common in all cases, this is common and this is also common. But you can see here is CO, one CO, and this is also one CO, and this is also one CO. But in this case there is no CO other, only one CO. Okay, and here you can see this is CO, but here is no more CO ligands, because CO ligand is pi acceptor ligand. This is pi acceptor ligand. Okay, and PR3 is strong sigma donor ligand. This is strong sigma donor ligand. Okay, sigma donor ligand. So that's why this type ligand will increase the electron density on metal, on Cr. So this type ligand, because these are sigma donor ligand, so they can increase the electron density on Cr metal or any central metal atom. Okay, but in this case this is pi acceptor ligand, so it will withdraw some electron density from the central metal, like in this case like chromium. So carbonyl ligand will withdraw the electron density from the chromium metal. Okay, so it will decrease the electron density on chromium. Okay, So now you can make a order, electron density order, electron density order. What is the electron density order? Here you can see 2 sigma donor, here 1 sigma donor, but there is no, in this case, no sigma donor. So where is the maximum electron density? In this case, definitely, because this CO will withdraw some electron density. Okay, so this is decreasing electron density on chromium, but it is increasing electron density on chromium. So that's why we are going to make an order of electron density, because electron density directly proportional to the basicity of the complex, corresponding complex. Okay, so in this case there is maximum electron density on the chromium, but in this case little bit less, but in this case very less electron density on chromium atom. Okay, because of CO. CO is pi acceptor, that means it is withdrawing some electron density from the chromium, but it is donating some electron density on the chromium metal. And here is only one chromium, one electron withdrawing group, but 2 electron donating group on the metal. So that's why in third case there is maximum electron density on chromium elements. So that's why the basicity order, basicity order. What is the basicity order? Basicity directly proportional to the electron density, according to this concept. Basicity directly proportional to the electron density on the metal. So that's why this order will follow similar trend of electron density. So basicity of third complex will be high as compared to second, and second will be higher basic as compared to first. So this is the accurate order of the basicity. Similarly, if you want to make a basis acidity order of this, but it is negative charge, so there is no acidity concept, it is only for basicity. But as we know, the acidity and basicity directly proportional to each other. So that's why if you want to make a acidity order, acidity will be high of first complex, okay, just opposite to basicity order. So this is an example based on this concept. So today we discussed the metal carbonates, acidity and basicity, and because metal is negative charge, so it can act as a base and it can also act as a nucleophile. Okay, and we have already talked about nucleophilicity, nucleophilic attack of metal carbonates. Today we discuss the basic character, basic properties of metal carbonates, and how can we decide the basicity of metal carbonates complexes. We know that basicity is directly proportional to the electron density on central metal atom, and another thing is that electron density is also dependent on the donation power of electron density. Now we have already discussed this point, basicity directly proportional to the electron density, by taking an example. Now we are going to understand the second point, basicity directly proportional to the electron donation power of central metal atom. Which central metal has maximum electron donation power, the complex, the corresponding complex will be highly basic in character. Okay, now we are going to take an example of this concept. On this concept, you can consider an example of TCRE, and I mean you can make an example of from top to bottom, because if you go from top to bottom, the size of metal will be increased. So that's why the tendency to lose the electrons of metal will be increased. So that's why you can say that the donation power of metal atom will be increased from top to bottom. So that's why bottom metal carbonylates complexes will be more basic as compared to top metal carbonylates complexes. Okay, so now we are going to take an example like suppose you have a metal carbonylates complexes of MnCO whole 5 1 negative. Okay, so this is a metal carbonate, and second transition element of this family, this is TC and this is RE. So you can make an example to understand this concept, and this is CO whole 5 and 1 negative. Okay, there is only one difference, because here is carbonyl, 5 carbonyl, 5 in each case. Okay, and negative charge 1 negative charge in each case. Okay, you can make like this. it is indicating that this negative charge is on the coordination sphere of this complex. Okay, but there is a difference. This is first transition series element, this is second, and this is third. That means you are going to, if you moving from here to here, this is bottom. Okay, this is bottom, this is top in periodic table. In periodic table you are moving in group from top to bottom. Okay, so that's why size of metal will be increased. Okay, so that's why to lose the tendency to lose the electrons from valence cell will be increased. Okay, will be increased. So you can say that this complex has maximum tendency to lose the electron, because if there is a electron donation power increase, that means you are going to capture the proton. Okay, so it has maximum tendency, maximum power to attack the proton from the reactant species or solvent or solution. Okay, because it has maximum electron density, that means it can easily remove electron density, and that electron density can be utilized to attract the proton from the reactant or solution. So the basicity of this will be high. So you can say that when we move top to bottom in transition elements or in a group, then the tendency to lose the electrons will be increased because of size of metal will be increased. So that's why nuclear charge will be less effective from top to bottom. So electron can be easily removed from the metal, and that electron can attract the proton from the reactant species or solution. So that's why the basicity will be high, because basicity directly proportional to the electron donation power. So you can say electron donation power is going to increase from top to bottom in a group. Okay, so that's why the basicity directly proportional to the electron donation power. So basicity order, if this is complex first, this is second, and this is third complex. So third complex is more basic as compared to first, and first is more basic as compared to second is more basic as compared to first. Okay, so these are two basic concepts, and you can apply to define the basicity and acidity of metal carbonylates complexes. Okay, we have another one example to understand more this concept. Suppose you have a complex. Suppose you have a complex cobalt CO4 1 negative, and you have another complex is CP means cyclopentadienyl ligand, like this. This is CP ligand, and you have Fe and CO4 twice and 1 negative. You need to design the basicity order. Which one is more basic from these two metal carbonylates complexes? So you can see here, this is if you take this complex, you can see this is D7 case, right? D7, 3D7 and 4s2, right? And this is 3D6 and 4s2 metal. But in this case, here is 4 pi acceptor ligand, but here is only 2 pi acceptor ligand, but one is sigma donor ligand. So because this ligand is CP cyclopentadienyl ligand, and this ligand is sigma donor ligand. Okay, so that's why it will increase the electron density on Fe atom. It will increase the electron density on Fe atoms. So that's why in this case metal has maximum electron density as compared to this, because CO, 4 CO and 1 CO is pi acceptor. Pi acceptor ligand. It is electron withdrawing group. Electron withdrawing group. This is electron withdrawing group, right? Electron withdrawing group. And this is electron donating group. Electron donating group. This is electron donating group. Doesn't matter, it has D7 electron, this is D6 electrons. Negative, negative is same. But in this case, there is maximum pi acceptor. 4 ligands are pi acceptor ligands. 4 groups are electron withdrawing groups. So that's why they will minimize the electron density on cobalt atom. But in this case, this is sigma donor ligand. Also, you can say that the delocalization electron density of cyclopentadienyl will be donated to Fe atom. So that's why this is electron donor ligand, and it will increase the electron density on Fe atom. So it is more basic as compared to this complex. Okay, no. So this is the basicity order. This is more basic as compared to this. So you can make a order. If you have any question related to basicity or acidity of metal carbonate complexes, you just need to remember the basicity directly proportional to the electron density on metal atom, and another thing is that electron basicity directly proportional to the electron donation power of the central atom, and electron donation power can be decided on the basis of size of metal. From top to bottom it will increase, so that's why basicity of metal carbonates will also increase. And another factor, electron density, you can make some comparison between many complexes on the basis of electron donation group and electron withdrawing group, that is electron pi acceptor group and electron sigma donor group. Okay, so then you can make a comparison and you can solve some problems related to basicity and acidity of metal carbonates complexes. Okay, thank you very much. In next lecture we will study about metal hydride complexes, which is analogous complexes of metal carbonates complexes, because this negative charge, if attract proton, then that proton will attach with metal and the obtained complex will be metal hydride complex. Okay, so in next lecture we will discuss about metal hydride complexes. Okay, thank you.